So here's a typical combustion problem as realized in your ALEKS homework system. And it's a tricky problem for students to master. So let's just take a look at the data and go through this step by step so that we understand how we can get to the promised land of the solution. What are we told here? We're told we have 1 gram of some compound X. And it's made of carbon, hydrogen, and maybe oxygen. It has a molecular molar mass of 70 grams per mole. We burn it completely in excess oxygen, and the mass of the products is carefully measured. We get carbon dioxide, 3.14 grams, and water, 1.29 grams. So this compound X is some combination of carbon and hydrogen for sure, and oxygen is a maybe. If we think about what's going on in this reaction, all the carbon in the CO2 must have originated from compound X. The same goes for all the hydrogen in water. All of it must have originated from compound X because that was burnt. Oxygen becomes a little trickier because we potentially have oxygen in our compound X, but it's also being burnt in oxygen. So oxygen here and here could potentially come from 2 different sources. That's what makes this problem kind of tricky. So let us begin with the easier part, which is figuring out how much carbon and how much hydrogen was in this compound that we burnt in oxygen. That's the first goal. So we can take our 3.14 grams of carbon dioxide, we can divide it by the molar mass, but we don't really want moles of carbon. We want moles of carbon dioxide. We want moles of carbon. So we use the mole to mole ratio, and we discover that we have 0.713 mole of carbon. Now, in order to get grams of carbon, we're going to multiply by the molar mass of carbon, and we're going to find out that we have 0.857 grams of carbon. So we have 2 pieces of data that we're going to need here. We're actually going to need this piece of data and this piece of data before we're done. Next up is hydrogen. So we start from 1.29 grams of H2O. We divide by the molar mass of H2O, but if we want to get at hydrogen, this is an important step here. There are 2 moles of hydrogen for every 1 mole of H2O. If you don't include this mole to mole ratio here, you will get an incorrect answer. So this gives us that there are 0.143 moles of hydrogen in 1.29 grams of H2O. When we multiply by the molar mass of hydrogen, we get that we have 0.144 grams of hydrogen. Okay, so again, we're going to need the mole and we're going to need the grams before we're done. So the question here is, if we started with 1 gram of compound X and we subtract from that the gram quantities that we just calculated, anything left over must be oxygen because we have 1 gram of the compound and it's really a zero-sum game, right? So if we take 1 gram of compound X and we subtract the grams of carbon that we just calculated and the grams of hydrogen we just calculated, we're going to find that we actually get something very close to 0. So in this instance, there is no oxygen in compound X because the grams of carbon and the grams of hydrogen add up pretty much exactly to 1 gram. Now, this isn't always true in these problems, but in this case it is. So now how are we going to get at the empirical formula? Well, the same way that we always do. We know we have 0.713 moles of carbon and 0.143 moles of hydrogen. We can use that to derive an empirical formula. How? Well, we go through and we divide as we always do by the smallest number. What's this going to give us? This is going to give us CH2. The empirical formula is CH2, and that, if we do the mass, is 14.03 grams per mole. However, we're told in the problem that the molecular molar mass is 70 grams per mole, so we have more work to do. We take our 70 grams per mole, we divide by 14.03 grams per mole, and we find that that ratio of molecular molar mass to empirical molar mass is 5:1. That means we must take our empirical formula and multiply it by 5 to give us a final molecular formula of C5H10. Now, in some of these problems, you're going to find out that you do have oxygen, that this won't be 0. So now you have to think about what you would do in that case. You're going to have to take the grams of oxygen, if any. This is a 0, right? This is not oxygen. If oxygen, you will take the grams of oxygen, convert it to moles, and include that in your empirical formula, and go through the same process of using the empirical formula to derive the molecular formula given its molar mass. And that's all.